So in our last video, we learned about time constant tau, and I mentioned that it's very important because it helps us to understand a very important concept in control system, which is called control bandwidth or bandwidth of the control system. So I mentioned, said if you have the first order control system, as I show here, I mentioned that this is a static gain and this is a tau we're talking about, which is measured in seconds. And this is static gain. So from this, mathematically speaking, bandwidth will be equals to 1 over tau. And this will be measured in radian per second. It can also be measured in cyclic frequency, which is in hertz, in the following means. Omega bandwidth equals to 2 pi f bandwidth. So f bandwidth here now will be equals to omega bandwidth over 2 pi. So this one can be measured in hertz, as we know. So from our first order control system shown here, if we do a board plot or a plot diagram here, omegas, this is our magnitude, we will have the following characteristics. So if this one here, it's my omega bandwidth, it means if I go up here, and then if I go to the left, to my magnitude, this will give the magnitude of minus 3 decibels. So what is a system bandwidth? System bandwidth tells us how fast can a system track a given input before the system starts to attenuate. This means if I have input which varies in time, the maximum frequency of this input should be less than my system bandwidth in order that the tracking process take place. Otherwise, the system will be degraded. Let's see an example. Okay, as an example, I have this different system mounted in simulink. The parameter are here defined. Omega in is the input frequency for this sinusoidal input. Then omega 1 up to 3 is for system 1, 2, 3. Then here we calculate tau. As we said, tau equals 1 over omega. So here I calculate tau 1, 2, and 3. So let's simulate and see the results. Before that, as you can see here, omega 1 is 10 times the input frequency. Omega 2 is 5 times. Omega 3 is the same as input frequency. So let's see if we can see what we expect. After doing the simulation, we obtain the following results. Here, the first column are my all systems excited with a state function, and here all systems excited by sinusoid function. So as we can see here, at the first plot, the top left, almost 30 seconds, the system has already able to track its input. The second one here, it's faster, but not faster than the first one. And the third one here, we see that it's slower. Why? It's because its bandwidth is too small. Okay. If we come to the sinusoidal inputs, as you can see, the first top right, you can track my input almost with 0 error. And the second one here, the error is minimum. But the third one, as we can see here, the system is not able to track the input. As we mentioned before, the system is already being degraded. So if if you don't see it well, let me copy the plots and put them in paint. So I have copied the plots and inverted the color so that it can be seen. See, yeah, it's clear that the first one are the best because the bandwidth is too higher, the 10 times my my input frequency. The second one are better, but the third one are worst. So why? So why do we have, or why are we interested to study or to know the system bandwidth? It's important because to help us during control system design, like gain tuning and some other stuff. Thanks.